Hi everybody. In this video I'm going to discuss two important aspects with respect to signals, which is the mean or average value and the RMS value or effective value. Let's start with defining two signal types. First of all, we have the DC or direct current signals, and on the other hand we have alternating signals, which we also call AC signals. DC signals are signals with only one polarity or signal direction, so they be either positive or negative. And they can be constant or they can be varying. Here we have an example of a DC signal because it has only a positive polarity. It doesn't change, it doesn't go underneath the zero voltage line. So it's a DC value and it is a constant value. Here we have a varying DC value. Again, it's DC because it does not cross the zero voltage line. So it has one polarity, only a positive value. AC signals do not have one direction or signal direction. They always cross the zero voltage or zero current or whatever the unit might be, the zero line. It might be either periodic or non-periodic. In this example we have a periodic voltage because after this time the signal repeats again. This is what we call the period time. There are a couple of aspects which are important with respect to periodic signals. As I discussed, the period time over here, which is the time after which the signal repeats itself again. Based on that period time, we can define the frequency, which is f, and f can be defined as 1 over the period time. And the unit of frequency is hertz. So it's 1 over second, and another unit is hertz. We can also, based on this frequency, the angular frequency, omega, which is 2 times pi times f. And the unit for angular frequency is radians per second. Why is it multiplied by 2 pi? Because every circle we get, so every revolution in a time unit, every revolution, the angle is 2 pi, so the angular frequency is 2 pi times that frequency. Other important parameters in a periodic signal are its maximum value, or even more important, the top or peak value between the highest and the lowest value. So now first of all let us discuss the mean value or average value. When I have a signal over here and I want to define or calculate the mean value, I'm going to divide the signal into very small parts. And I make these parts as short as possible. And I say, well, during these parts, my value is of a constant level. Well, you can see from a deductive point of view, I didn't make these pieces too small, but when they're small enough, we can say, well, during these pieces, my value is constant. Now we can define the mean value, which is the sum of all of these values during these pieces. So u1, u2, u3, up to un when we have n values, and then we divide that summation by the number of pieces we defined. So when we have 10 pieces, we have u1 plus u2 up to u number 10 divided by 10. And then we have the mean value. Now let's do it in an example. We have a signal over here, which is constant for 1 second to a value of 5 volt, and then 4 seconds this value is 0. So the mean or average value is 1 plus 0 plus 0 plus 0 plus 0. We have 4 pieces over here, 1 piece over there. We add them all up and divide it by the number of pieces, which is 5 in this example, and then we get an average value of 5 plus 0 plus 0 plus 0 plus 0 divided by the number of pieces divided by n, and then we get 1 volt. In real life, we want to make these pieces as small as possible, and the the mathematically operation we are applying in that situation is taking the integral. Well, when we want to do that in an example, we take for an example this sine and we want to take the mean value of half of this sine. It doesn't matter, it doesn't make any sense to calculate the mean value of a whole sine because you can see that this positive value equals this negative value, so the average or mean value of a complete sine is always 0. So let's calculate the mean value of half a sine wave. Suppose this signal which we are going to use has this expression. U is 10 times the sine of t. So 10 is the top value or the maximum value over here, and the period time is 2 pi, which is 2 times 3.14, which gives us 6.28 seconds. And when we want to calculate the mean value of half the sine wave, we have to take the integral of half the sine wave and then divide it by this period, which is pi, 3.14, and then we have the mean value. So let's do it. We take the integral of this signal, so the integral from 0 to pi, from 0 to pi, of this signal 10 times the sine of t, and then we divide it by pi, or we multiply it by 1 over pi. Because 10 is a constant value, we can take it up front the integral, and then we get 10 over pi times the integral from 0 to pi of sine t integrated to the time. Well, let's work it out. The integral of a sine is minus the cosine. So then we get minus the cosine of t integrated across the boundaries 0 to pi, 0 to pi, and then multiply by 10 over pi. So let's work this out. Here we get minus the cosine of pi, here it is, minus the cosine of 0, fill it in over here, so minus cosine of 0 and multiply the whole by 10 over pi, which was indicated over here. Well, the cosine of pi is minus 1, so minus 1 is 1. The cosine of 0 is 1. Minus times minus is plus, so it's 1 plus 1 multiplied with 10 over pi, and it gives us a solution which is equal to 10 times 2 over pi. In general, the mean value of half a sine wave is always the top value, in this example 10, times 2 over pi. So when you have an amplitude of 5, you get 5 times 2 over pi. When you have an amplitude of a billion, then you get a billion times 2 over pi. That's the mean value. Now let's look to the effective value. The effective value of a voltage is the value of an imaginary constant DC voltage which yields the same heat generation and the same resistance in the same time. Well, that's a lot of stuff, but let's work this out. What we are going to do, first of all, in this picture again, and then mathematically, is calculating that effective value. And the first step we are going to do is we divide this signal again in a number of small pieces. We did that again over here. And then all the constant values during these pieces are taken quadratic. So we take the square of all values during these pieces. And then we take the RMS value, the root mean square value of that signal. That's why American people often don't talk about effective value, but they talk about root mean square values, because that is what we are going to do mathematically. Well, we started off with taking the squared values during every piece in this signal. Then that's where we started with. Then we take the mean, and afterwards we take the root of that signal, and when we have done that, we have taken the RMS value or the effective value of that signal. Well, let's work it out. We had the signal, and we have the squared values during every period. Um, Now we are taking the RMS value, so during every uh, period over here, so every piece over here, we take the squared values. Then we are taking the m, which is the mean, and we can calculate the mean by summing them all up and dividing them by the number of pieces which we have defined over here. And then we take the root, which is the square root, which is written over here. And then we have taken the RMS or effective value. Well, let's work this example, work it out, and then we can do it, for instance, with this graph, in which we have a signal which is 2 volt during 1 second, then during 2 seconds it's 4 volt, again it's 2 volt during 1 second, then it's minus 2 volt during 1 second, then it's minus 4 volt during 2 seconds, and it's minus 2 volt again during 1 second. And then this signal is repeated again. So my total period time is 8 seconds, and I have divided it in 1, 2, 3, 4, 5, 6, 7, 8 pieces. We are taking the effective value, so we're taking the RMS value. So we start with taking the square in every piece which we have defined. Well, this is 2, so this is squared, 2 squared. Here in this piece it's 4 squared, here is 4 squared, here it's 2 squared, minus 2 squared, minus 4 squared, minus 4 squared, minus 2 squared, and then we have used the complete period. Then we add them all up and divide it by the number of pieces, which is 8. So then we have the mean value, and then we take the square root of it, and then we have taken the complete RMS value. And when you work that out, you get the value, the square root of 10, which is 3.16, and the unit of the signal was volt because it was a voltage. So that is the effective or RMS value of this signal. When we do it correctly mathematically, then we have to take these pieces as small as possible, so we have to use the integral again. So let's take the effective value of a sine wave. And in this case, when taking the effective value of a sine wave, we also can take the effective value of half a sine wave, because we start off with taking the square from the signal, and then this negative part becomes a positive part. So let's take the effective value or RMS value of half a sine wave. So this is my signal again with this signal definition. U is 10, which is the maximum value or the peak value over here, times the sine of t. The period time was 2 pi seconds, and half the period time was pi seconds with it, which is 3.14 seconds. Now we are taking the RMS value of this signal. So first of all, we take the square of it, so the square of this signal. Then we take the mean, which is the integral from 0 to pi, of this squared signal, and divide it by 1 over pi, because we have to take the mean. So again, the mean is the integral, and then divided by the complete time, the integration time over here, which is pi in this example, and then we take the root from the RMS value. And when you work that out nicely, which I'm not going to do in this presentation, then you get the result, which is 10 over the square root of 2, which is equal to 10 times 0.5 times the square root of 2. And that is always the RMS value of a sine. RMS value of a sine is always the maximum value or the peak value, situated over here, times 0.5 times the square root of 2. Or you can define it as the maximum value over here divided by the square root of 2. That's always the case when taking the effective value of a sine wave. Well, two more terms which I want to discuss in this voltage, which are used in electronics. One of the terms is the form factor, FF, which is the division of the effective voltage by the mean voltage. So it's a ratio between these two voltages, the effective voltage and the mean voltage. Another important term which is used in electronics is the top factor, Ft, which is the relationship, the ratio between the maximum value or the peak value divided by the effective voltage or the RMS voltage. Well, you can do it for a lot of signals. The most important one is the sine because, yeah, that's the signal which we see very often. For instance, it's the voltage from your plug system, your voltage system in your building or in your house, your 230 volt system. That's a sine. So from that sine, we have seen that the mean value of half a sine is this expression, and the effective or RMS value is this expression. When you have calculated the effective and the mean values, you can either calculate the form factor or you can over here, or you can calculate the top factor over here. Well, that's all with respect to signals. I hope you enjoyed the video and see you next time.